Design and analysis of low-power reversible adder/subtractor circuits. Abstract. In recent years, reversible logic has become a promising technology in the areas of low-power VLSI design, nanotechnology, quantum computing and optical computing. The performance and reliability of digital systems which are now implemented using conventional logic gates can be enhanced by the usage of reversible logic gates, which pave for low power consumption and lesser quantum delays, thus increasing the speed of computation. Adder/subtractor circuits form the fundamental block in the arithmetic and logic unit of processors and other digital logic programmable devices. The performance of a digital system, its speed, and throughput depend critically on the way these circuits are designed. Adder circuits are used in the graphics processing unit, GPU, of computers for graphics applications to reduce complexity. Any way to enhance the performance and computational speed of these circuits will pave way for a better ALU. Incorporating the concepts of reversible computing in the design of adder/subtractor circuits can significantly enhance the performance and speed of operation of digital systems. In this paper, two existing adder/subtractor designs and a novel design are compared, analyzed for different bit lengths, 1,8, 1632, 64. Detailed analysis of reversible logic design parameters, power consumption parameters, and FPGA utilization parameters is carried out. These designs are analyzed and simulated using the Xilinx Vivado tool and implemented on Zedboard Zynq Q7000 Evaluation and Development Kit, XC7020CLG484-1. The proposed design outperforms the existing designs. Keywords: reversible ALU design, reversible logic, reversible adder/subtractor, low-power VLSI design, high-speed adder. Introduction. Over the past few decades, phenomenal growth has been achieved in the design of computers and other digital logic processing devices like mobile phones, calculators, etc. Incorporating several millions of transistors into a single chip has enabled computations and operations to be efficient and fast. However, having very high transistor densities will lead to an increase in power dissipation. Existing technologies like CMOS will reach their boundaries soon as believed by today's researchers. Power dissipation and vulnerability to computing errors are the most important problems associated with the existing technologies. Reversible logic is believed to be a prominent technology that could alleviate the drawbacks of the existing technologies. Reversible circuits are called lossless circuits, as there is neither energy loss nor information loss. These circuits are very attractive in applications where extremely low power consumption is needed in areas ranging from communications, low power VLSI, very large scale integration, technology, DNA computing to nanotechnology. Furthermore, reversible logic is very useful in quantum computing where the quantum evolution is inherently reversible. Arithmetic circuits such as adders, subtractors, multipliers, and dividers are the quintessential blocks in a data processing system. Dedicated adder/subtractor circuits are required in several digital signal processing applications. Reducing the number of reversible gates required to realize a circuit, quantum costs incurred and garbage inputs/outputs are the focus of research in reversible logic circuit design. In 1, it is depicted that the amount of energy, heat, dissipated for every bit operation that is not reversible is given by KTLN2, where K is the Boltzmann's constant, 1.3807 times 10-23 JK1, and T is the operating temperature of the system. For T equal to the room temperature, 300 K, KTLN2 is approximately equals 2.8 times 10-21 J, which might seem as small but it is non-negligible. For example, assuming that all the 1.75 billion transistors in a processor, example Intel i5 core, dissipate heat at a rate equal to the processor's operating frequency, 2.5 GHz, then the processor would consume a power of approximately 2.5 times 10 to the power of 9th, x, KTLN2, x, 1.75 times 10 to the power of 9th, equals 12.258 MW, assuming that the room temperature is 300 K. The loss incurred is not tolerable in the design of ultra-low power consuming devices. Furthermore, Moore's law states that speed and capability of computers can be expected to double every 2 years, as a result of increases in the number of transistors a microchip can contain. The increase in transistors will lead to further power consumption and power dissipation due to information loss. If this goes on, there will be an intolerable amount of heat dissipation by computer systems. The advent of revolutionary technologies in computing is the need of the hour. One such technology is reversible computing. 2-3 in 1973, C.H. Bennett concluded that no energy would dissipate from a system as long as the system was able to return to its initial state from its final state regardless of what occurred in between. In 4, it is shown that the theory of reversible computing is based on invertible primitives and composition rules that preserve invertibility and the constraints to be met with deal with both functional and structural aspects of computing processes. The laws of physics won't have an impact on the reduction in the size and quantum behavior of computers as depicted in 5. Reversible logic can be defined as thermodynamics of information processing. Hence, it is used to reduce the power dissipation by preventing the loss on information. 6. It is shown in 7 that parallel adder/subtractor can be extended to design low-power reversible ALUs, multipliers, and dividers. In 8, 4 designs for reversible full adder circuits and their implementation in CMOS logic and pass transistor logic were presented. A detailed description on reversible computing, quantum implementation of reversible gates, challenges and promising features of reversible logic in. Furthermore, it delineates how reversible logic technology will pave way for achieving ultra-low power computing. Presents a detailed analysis of FPGA utilization parameters and power parameters of reversible logic designs. 2 designs of adder/subtractor circuits using WG gate and DKG gate are proposed in a serial adder/subtractor circuit constructed using 4*4 DKG gate, and an analysis on reversible logic parameters is carried out in a 8-bit adder-subtractor circuit using reversible approach for Xilinx Spartan 3E FPGA is proposed, simulated, and synthesized in a novel design of ALU is compared with an existing design. In 3 designs using TR, Paris, and Feynman gates were proposed and compared them in terms of quantum cost, garbage outputs and gate count. One of the designs is considered as existing design 1 in this paper. A 8-bit parallel adder/subtractor using DKG gate and dual key pair gate, DKPG, in Xilinx ISE design suite is implemented in. Section 2 of the paper explains the terminologies associated with reversible logic, power consumption parameters like static power, dynamic power, etc., and FPGA design and utilization parameters like LUTs, nets, etc. Section 3 of this paper presents some of the important basic reversible logic gates, their quantum costs, and quantum representations. In Section 4, a brief overview of adder/subtractor circuits. Section 4 presents the existing design 211 and the proposed design. The circuit diagram, RTL schematic, various logical and arithmetic operations of both designs are also provided under it. Section V of the paper consists of simulation results of the designs for different bit lengths, waveform results from Xilinx Vivado tool, and also charts and tables of comparison of parameters like gate count, number of garbage outputs, power parameters, the delay incurred, and FPGA utilization parameters. Section 6 presents the conclusion of the paper. Terminologies. A reversible function. Comparison chart of gate count, number of garbage outputs and quantum cost of existing and proposed designs. Shows the comparison between the existing designs and the proposed design of the 64-bit reversible adder/subtractor designs. It can be depicted from the Fig. 41 and tables 2, 3 and 4, that existing design 2 uses a fewer number of reversible logic gates, has fewer number of garbage outputs, and incurs the least quantum cost in comparison with the other designs. Furthermore, it is understood that the difference between the proposed design and the existing design 2, in terms of quantum costs, is not that significant, and also it can be seen that the proposed design outperforms the existing design 1 by a good margin. Fig 44. Comparison chart of delay incurred for 1,8, 64-bit RCA/RBS of the 3 designs. Based on Table 8, the comparison of delay between 3 designs of reversible adder/subtractor circuits is made. Based on the result as shown in Fig 44 and in Tables 2, 3, 4, and 8, it can be concluded that the proposed design shows higher reductions in propagation delay as compared to the existing designs. 6. Conclusion. In this paper, a novel adder/subtractor design has been proposed. The proposed design is compared with 2 existing designs. These designs can be used to construct n-bit adder/subtractor circuits by cascading n 1-bit circuits. The designs have been simulated, analyzed, and verified using Xilinx Vivado tool. They are implemented on Zedboard Zynq Q7000 Evaluation and Development Kit, XC7020CLG484-1. The performance and power consumption of the designs are compared with one another for different bit lengths, 1,8, 1632, 64. The quantum cost, number of garbage outputs, LUTs, nets and leaf cells are also evaluated. The simulation results illustrate that the proposed design outperforms the existing designs in terms of FPGA utilization parameters, power consumption, and incurring delay. A complete reversible computer architecture can be designed with the help of the proposed design shortly. Reversible adder/subtractor circuits can soon find their application in calculators, mobile phones, and other ultra-low power consuming devices. Furthermore, The proposed adder/subtractor design can serve as a basis for the design of sequential reversible circuits.